Hello everyone, welcome to the OneClass channel. My name is Millen, and I am a software engineering student at Carleton University in Ottawa, Canada. Today, I will be going over some commonly asked physics questions at both the high school and university or college levels. If you are interested in getting help with your homework, or if you're interested in tutoring, check out the links in the description below. Cool, so to get this physics party started, I'm just going to switch my screens real fast. And let's get this show on the road. Awesome. Okay, so the first question that we have on the menu today is asking us a proton with a speed of 3. Okay, well, what this really means is, I'll write it out. So we're mentioning our proton speed, right? So let's just call that V. P for proton. It's 3.0 times 10 to the power of 5 meters per second. Okay, I'm pretty sure it's really just a formatting issue that's going on with all these spicy looking characters. But okay, so this is our speed. This is the speed of the proton, and it's moving perpendicular to a uniform magnetic field, which is 0.2 teslas. Okay, so let's write that in. Our B field, which is magnetic field, is 0.20 teslas. So this is magnetic field. And this is our proton speed. Okay, and it will follow which type of path? It's going to follow a circular path, because we know that charges moving through magnetic fields always follow circular paths, assuming that the charges are moving, that is. And include, we want to find the radius, and then we got some other information, like the charge of a proton. So here we have Q. Let's call that QP, charge for a proton. This will be positive 1.6 times 10 to the negative 19 coulombs. So this is a proton charge. And that's just a nice thing that you could memorize. It's not mandatory that you memorize it, but you're going to see this number so often that it really is in your best interest to, keep it in the mental reservoir. Okay, so that was given by the question, is the charge of a proton. And we also have the mass of a proton, and that is 1.67 times 10 to the negative 27 kilograms. So let's call that MP. So this is 1.67 times 10 to the negative 27 kilogram. Now, please excuse the formatting here. I'm pretty sure this could be just a technical issue on the UTF encoding. That's really deep into like programming stuff. You don't really need to worry about this, but yeah. So this is the proton mass, and what we're trying to find here is the path of proton travel, and it's asking specifically the radius and radius. Okay, so this is our question. And the first thing that we want to mention is, I'll write this in a different color, maybe purple. Important. This is a rule that we always know about charges moving in magnetic fields. So, charges in magnetic fields always follow circular paths. Okay, now let's think about for a minute, why is this even the case? Okay, so I'm going to scroll down a bit, but all this information up here will still be relevant. We'll come back to that in a moment. But here is the equation for magnetic force. So let's call that FB. Why do we use B for magnets? Just because I think M, like we can't really use M because M is used for mass. So mass and magnets, both using M, that would be confusing. So we're going to use a completely unrelated letter, but it's okay. You just got to get used to it, and it's really not that bad once we get familiar with it. Just remember, B typically refers to magnetic fields. Okay, so the magnetic force on a charge is the result of the charge itself multiplied by the cross product of velocity multiplied or cross product with the B field, which is the magnetic field. Okay, so suppose that we have a charge like this. Let's call that Q, and it's going this way. And let's say the B field is going, or this is the V, and let's say the B field is going into the page. Or coming out of the page, that's what I meant. So it's kind of like this dot and X notation means in or out of the page. So dot means out of the page. X means into page. And you can kind of think of it like, you know, we have these arrows, right? And these arrows have their little like quills at the end to help them like be aerodynamic. So into the page, you're kind of looking at the tail end, the quills of an arrow, and out of the page, well, you're looking at the tip of the arrow. So in this case, we're looking like this. So if we want to do the cross product here, we want to follow the right hand rule for cross product. And that essentially is saying like our index fingers are going to go towards the velocity, the first thing that we're cross producting. Our palm is going to go towards the B field. In this case, we're going out of the page. And our thumb is going to be in the direction of the result. So in this case, the result would be down this way. FB. Okay, but just a moment later, that FB is going to cause, draw this in a different color, maybe in lighter blue. So a few moments later, Q is going to be like this, and the velocity will have changed because the velocity has to change. You know, because the force causes the velocity to change. Force causes an acceleration. An acceleration is a change in velocity. The magnitude of the velocity does not change. So if it's originally going at like 100 kilometers per hour, it's still going 100 kilometers per hour. But the direction changes. That's what happens with this magnetic force, okay? So now if we recalculate the magnetic force at this point, at this lighter blue Q, we can see like, assuming like the magnetic field is like all throughout and it's always constant. You always have to assume that the magnetic field is constant for circular motion. So the B field is going to be the same. So we want to curl our, well, first we want to have our fingers follow the velocity, and then have our fingers curl towards like out of the page. That's with the B field, and we could see that our magnetic force is where our thumb is pointing, which is here. Okay, so you can see at different the direction of magnetic force FB is always perpendicular to velocity and this leads to circular motion. It's kind of like centripetal motion. Like if you ever had maybe a situation like this, let's see if I can get like a wire or something like that. Aha. So this is a patch cord to my guitar. Guitars are really cool. So, you know, if I'm spinning it around here like this, you can see that the acceleration, the reason why like the tip itself is always going the same velocity as it's flying around here, but the force is going towards the center of the spin to make sure that this is not flying away. And if I were to suddenly let go of this, it would just keep flying in a tangential path, because once I let go, there's no more centripetal force. And that's what this magnetic field is acting, or this magnetic force is acting as. The magnetic force is acting as a centripetal force. Okay, let me write that in to make that super duper clear. So, magnetic force acts as centripetal force. Okay, so that kind of answers the first part of the question here, is when it's asking us what type of path will this particle, proton more specifically, follow. We know that it has to be a circular path. Okay, and yeah. And in this circular path, we know that the magnetic force is going to be equivalent, or is going to be acting as a centripetal force. Okay, so we want to say this. Okay, well, we can write an equation for that. So magnetic force is equal to a centripetal force. And we can represent that with variables like FB for magnetic and F centripetal for, or FC for the centripetal force. Awesome. Now let's rewrite them in terms of what they're made of. So we know that FB is going to be Q VB. Since we don't really need to worry about the cross product nature of it right now, we can kind of treat it as a multiplication because we don't have like directions to worry about. But if you want to be more formal, just know that you're going to want to use the cross product unless you're doing like a 2D scalar analysis or a complete scalar analysis. Okay, so we have Q VB, which is equal to the centripetal force. And as we know, the centripetal force is mass times velocity squared over radius. Okay, now, so we know that it's going to be a circular path, and it's asking us to pretty much get the radius of the circular path, because a circle is perfectly defined with just one thing. If you have the radius, you can define the circle. Okay, so let's do some quick algebra to isolate the radius r. Isolate r, or isolate radius r. And let's do it like this. So we can multiply both sides by r and get r on the upstairs, and divide both sides by QVB. So we can have something like this. R equals mv squared over, that v is kind of sketchy looking. Let's redraw that. V squared over QVB. Now, with some quick algebra, we can see that the v on the downstairs neutralizes the v squared, so it just becomes a regular v on the upstairs. So to rewrite this, this is really just mass times velocity over charge times the magnetic field. All right, so now we can just substitute in our numbers and we can call it a day on the radius. Okay, so we got our radius here. What's our m value? We know that it was the mass of a proton, so that's 1.67 times 10 to the negative 27 kilogram. Okay, awesome. Now we have just our velocity, and our velocity is 3.0 times 10 to the 5 meters per second. That is extremely fast, but that is reasonable to expect extremely fast moving protons because, well, in general, they do move quite fast. Because their mass is so low, we do expect them to be moving quite quickly. So don't be alarmed by these large numbers. And it's good to kind of have like a number sense to know, like, hey, I expect to see a certain degree of magnitude, like maybe 5, 6, 8 you probably wouldn't see, but the 4, 5, or 6 for the power of velocity seems reasonable. Okay, now on the downstairs we got the Q value, and we know that it's going to be the charge of a proton, so that's going to be 1.6 times 10 to the negative 19 coulombs, named after Coulomb. He was a pretty smart guy. And the last thing is B, which is our magnetic field magnitude. So that is 0.2 or 0.20 Teslas, named after Nikola Tesla, not named after the car. Okay, so we would just need to calculate this ASAP fast. Let me just grab my calculator. Boom. My TI-84 calculator. It's an excellent calculator if you're doing some advanced math. So let's calculate this whole thing. 1.67 times 10 to the power negative 27 multiplied by 3 multiplied by 10 to the power of 5 and divide that whole thing by 1.6 times 10 to the power of negative 19 multiplied by 0.2. And the result I got for that hopefully matches with this one. It does. So the result I had for this is 0.01565625 meters, which seems reasonable. And now let's do a significant figures analysis. So we know that everything was given with like all of our component numbers are 2 or 3 significant figures, so we have to give it to 2 significant figures. So to 2 significant figs, 2 SF, R is equal to 0.016 meters. Another way you could write that is 1.6 centimeters. That is a radius maybe about the size of maybe like a piece of corn. So that'd be like the radius of this circular path, about the size of a piece of corn, 1.6 centimeters. Pretty small, but pretty good. So yeah, the above solution. So it seems that we got the solution good here. Solution is good. Watch out for sig figs and mention of how charged particles moving in P fields follow circular path, and that centripetal equals magnetic force would be good. Cool.